Okay, we're picking up on 5.2, growth and decay. This is AP Calculus BC and Alanator here, and we have when you don't start at a value of t is equal to 0 for one of these growth and decay problems. So, example 3, suppose an experimental population of fruit flies increases according to the law of exponential growth. There were 100 flies after the second day of the experiment and 300 flies after the fourth day. Approximately how many flies were in the original problem? You're like, oh my gosh, maybe I need to read this again. Probably. But what we want to do is look at this. So we have this, I think I accidentally had a 2 there. Okay, and so we have KT right here, KT. Okay, 100 flies the second day, 300 after the fourth day. Approximately how many flies were in the original population, right? So we got to start somewhere. So we say this. So we have a T is equal to 2. T is equal to 2. And then we have Y is equal to 100, right? And here we have T is equal to 4. We'll go by days. And Y is equal to 300. Okay, so you have a couple of ordered pairs there to work with. Okay, so we start off like this. So we'll start with the 100. 100 is equal to C e to the 2k. T is 2, so we're going to make it 2k. Just split the order. Split the order, reverse the order. Okay, so that's our first one, right? And then the second one is 300 is equal to C e to the, and then k is still k, but t is 4, so we're going to make that 4k. So we have two equations, and if you notice, there's two variables. So what can we do? So what we will have to do is we'll have to somehow figure out how we're going to solve. We often love substitution with these kind of equations, right? So I'm going to use substitution, but what I'm going to do is I'm going to take the first equation. I'm going to say C is equal to, how about 100 over e to the 2k, right? There you go. There you have it. And then we can take and substitute it into the second equation if we like, or we can say here, C is also equal to 300 over e to the 4k. It makes no difference. So let me think for a moment what I want to do. So what I'm going to do is I'm going to just substitute it with these two equations. I'm going to take this C, this one right here, and I'm going to substitute it in the other equation. So I've got this. So I'm going to bring this one down here. I could set them equal to each other. I'm just not. So I have 300 is equal to C, which is 100 over e to the 2k. Okay, that's my C value that I'm using. And then I have times e to the 4k. E to the 4k. Okay, so now I get 300 is equal to 100. 100. We have the same base here. So remember, we can use that rule, a to the n over a to the m is equal to a to the n minus m, right? So we get e to the 2k, right? So then we can divide both sides by 100, and we get 3 is equal to e to the 2k. And then we use logarithms, right? ln of 3 is equal to ln of e to the 2k is just 2k. And so we get k is equal to 1/2. And you're like, part of you is like, does that happen all the time? Yeah, pretty much. You'll see that very soon. That's our k value, right? So now what are we going to do? So we are being asked approximately how many, so sometimes we get carried away, right? You get carried away sometimes. You're like, oh, I love this math. And it's just crazy, crazy. And what kind of people love math? So crazy people do. So we have approximately how many flies were in the original population, right? That's what you want to know. So you go back to your C. Your C is the original number of fruit flies. All right, so if you recall, oh, I'm missing a line there. So I could have swore there was a line there before. Somebody absconded with my fraction line. All right, so what we do, that's the end of the day bell, but I'm going to keep going. So we have C is equal to 100 over E, so we have to put the whole thing in here, 100 over e to the 2 times k. K is 1/2 ln of 3. Oh, this is too beautiful, right? So in the bottom, we have this is equal to 100. My pen is just deciding to conk out on me. 100 over e to the ln of 3 is what it is. Oh, you're like, wow, that's pretty fantastic, because when we get that, then that's 100 over 3, which is 33.3 repeating. So, I mean, we don't really have a third of fly unless you're dissecting flies. So, fruit flies. So what we have here is about 33 flies are in the original population. So 33 flies in the original population. Okay, everybody okay there? I can't hear you. All right, so there we go. There you have it. And now we have this last problem, Newton's law of cooling. Let Y represent the temperature in Fahrenheit of an object in a room whose temperature at a constant 60 degrees, whose temperature is kept at a constant of 60 degrees. The object cools from 190 in 10 minutes. Ooh, that's kind of important. Yeah, right. 190 in 10 minutes. How much longer, ooh, that's the question leading to the variable, right? How much longer will it take for the temperature of the object to decrease to 80 degrees? Newton's law of cooling is this. Okay, now, where M is the surrounding temperature. You know how when you have a cup of coffee and it's in the kitchen and you leave it sit? People sometimes think it's colder, and colder. It keeps going until it's freezing, but it really doesn't. It just goes to the temperature of whatever the room or whatever the surrounding area is. And T is the temperature of the object, okay? You go, what object? All right, well, it depends on the problem, all right? So how much longer? So Y represents the temperature of an object. So it's a very obscure object, something very anonymous. In a room whose temperature is kept at a constant, so we have the constant. The object cools from 100 to 90 in 10 minutes. So we know time is in minutes. How much longer will it take for the temperature of the object to decrease to 80 degrees? So we have the Newton's law of cooling. We have to get this equation all settled up so we know what to put where. We need some constants in here, right? But we don't have an equation yet. We have just the rate of change to start with. And notice I put a 60 in there because the surrounding, this is M. Okay, we start off like this. So the temperature of whatever it is capital T. T, lowercase t, is time. So you have to keep your capitals separate from your lowercase. Okay, so here we go. Okay, and we have, I'm going to do the separable differential equation. So I get 1 over t minus 60 is dt, so that the capital DT is equal to, I'm going to keep the k on the right-hand side, k, and I'm going to put the dt next to it. Then I'm going to integrating both sides. You can see that the t is in the front, so you have no chain rule, or not chain rule, but use sub to do here. So we get the ln of the absolute value of t minus 60 is equal to kt, integrate k, and you get kt plus c. When you do that, then on the left-hand side and the right-hand side, you're going to raise it to the power of e, if you think of it like this. Sometimes I just go ahead and invert it. And so many of you probably do. So I get t minus 60. And remember, I have this constant here. This is going to be e to the kt times e to the c power. So with that, I'm going to add 60. But if you're wondering about the constant, remember, this is going to become c e to the kt. And then I've got this t minus 60. So I'm not going to worry too much about the constant or the absolute value anymore, because I know that c can be a constant that changes things, and it will. Okay, so I have t minus 60. And so I end up with the equation. T is equal to c e to the kt plus 60. So now, if you notice, we still do not have the k. I still don't have the k. Hold on one moment. Just finishing up a video, okay? You can come on. I'm just finishing up a video. I'm going to leave it cracked there, okay? One of my students coming in to get some extra time in math. So hang on one second. So let me see, if you have, now that's our equation, right? So now we're going to substitute into that because we know some things, right? We know that the temperature is 100 degrees and it's going to go to 90, right? So we still have our 60 in there. So I could put that as 100 degrees is what says that the object cools from 100 to 90. So initially it's 100, right? So you have 100 is equal to, I'm going to put the constant first, 60, and then it's plus CE to the K times the time is 0, okay? So I did change the order there of the 60 and put that first, okay? So you have that, and then you change that to 40. Now subtract 60 from both sides is equal to C e to the k0. Well, that e to the k0 is just going to be 1, so is 40 is equal to our c value. And so now we have this equation. We have t is equal to 60 plus 40 e to the kt. Okay, now once we have that, then we can start now. It says it goes from 100 to 90 in 10 minutes. So then now I can find out what K is because I can put the 90 degrees is 60 plus 40, and then T is equal to 10 now. So I'm going to just make that 40e to the 10K. So now we can solve for the K value with that. So we subtract 60 from both sides, and that's equal to 40e to the 10K. And then I get 3/4. 30 divided by 40, 3/4 is equal to e to the 10K. And then now we're going to take the logarithm of both sides. So we get ln of 3/4 is equal to 10K, which gives us our K value. Our K is 1 over 10. K is going to be equal to 1 over 10. And like I said, you can take these and you can, it's ln of 3/4. You can take them and store the values if you like, or you could use them like that in exact form. A lot of times in a calc class, you do not have the luxury of having a calculator on a test, so you want to make sure you know how to just use them in exact form. So let's go ahead now. Now, keep in mind, our final question answer is we want to find how much longer will it take for the temperature to decrease to 80. So we want to put an 80 in there, but we have on our equation, we have everything we need for our equation. So we're going to start off like this. T is equal to, and then we have a 60 plus 40, 60 plus 40, and then it is e to the, and I'm going to run out of room here, so we're going to make this a little bit bigger. But so we pretty much put that into play here. So I have 40e, and it's to the 1/10, and it's 1/10 ln of 3/4 t. Okay, so we have everything in there, and so we're going to put the 80 in for t. Let me erase this 40 here. So we put the 80 in for t is equal to 60 plus 40e to the 1/10 ln of 3/4 and t. Where sometimes when you're writing these, you're thinking, I should have saved it, but just keep going with it. So subtract 60, you're going to get 20 is equal to 40e to the 1/10 ln of 3/4 t. Okay, and then after that, we get 20 is equal to 40, so we can divide both sides. So we're going to get a 1/2. We get 1/2 is equal to e to the 1/10 ln of 3/4 t. And now what we're going to do is solve for t. Take the ln of both sides, so you get the ln of 1/2 is equal to 1/10 ln of 3/4. We are almost there, kids. T. So once you do that, you're going to get the time. And remember, what are you asking for? How much longer does it take So now when you do this, you're going to get an answer for T that's based on 80, right? So you have to subtract how much time you've already spent. It already takes 10 minutes to go from 100 to 90. So now you're going in an additional, you have everything set up. You've got to go down to 80 now. So with this, we get T is equal to 10 times ln of, boy, oh boy, 1/2. And then that's going to be divided by, oh, I'm sorry, that's not 10. It is 10, but remember, that 10 is from when I divided by the right-hand side coefficient. So then that would flip up to the top, and then we would have ln, just the ln of 3/4 here. Okay, that would be our T value. So we get a T value of approximately 24.094, and that would be in minutes. But that's not the answer because remember, we have to take 10 minutes off of it that already occurred before this. So we would have 24.094 minus 10, and that would give us 14. It's so funny, my pen's lagging again. 14.094 minutes to cool. So it would take it to 80 minutes. I'm sorry, to get to 80 degrees, it would take it 14.094 minutes to cool. Okay, I'm going to leave this go for right now, and you guys have a good night. Alanator out, and I'll see you when I see you.